Hi everyone, today we're going to be extending our knowledge from what we learned about rectangular areas in class to some more general shapes. So shapes that aren't necessarily just rectangles or just trapezoids or any of the other formulas we've been using. If you hear any excessive noise, I'm very sorry about that. My neighbor is mowing his lawn right now. So if that gets into the audio, my apologies. Our objective for today is that students will be able to find the area of shapes by counting whole and partial unit squares. Essentially, we're going to be approximating areas that aren't perfectly rectangular. Common applications of this would be finding the area of an irregularly shaped room to figure out the amount of carpet you need to cover the floor. Right now, I would like you to pause this video and fill in this box with one more example of when finding irregular areas would be useful in everyday life. Thanks for working on that. Now we're going to move on to our first exploratory challenge. This exploratory challenge says, what is area in your own words? What is the area of the rectangle below, whose side lengths measure 3 units by 5 units? And explain how you figured this out. Now I'd like you to pause this video, write down area in your own words. What is the area of this rectangle? And then how did you figure this out? All right, so hopefully you had a good way to do this. I think the really common way that most of you would have done is to say area is length times width, which is 3 times 5, which is 15, right? That's what I expect that most of us would have done. But one other way that we could do this problem is by making a grid of unit squares and then counting up how many units do I have. So unit square is a square that has both a length and a height of 1, right? So that means that the area of this little square here is 1, right? So if I make a bunch of unit squares all over my grid, all I have to do is count these to figure out how many units I have, because this is 1 unit, now this one beside it is 1 unit, this one beside it is 1 unit, all of these are 1 unit. So if I count all of these, I get 15 units, which is the total size of my rectangle. Our second exploratory challenge says, what is the area of the rectangle below whose side lengths measure the square root of 3 units by the square root of 2 units? Use the unit squares on the graph to guide your approximation. So here you're just estimating what is the size of this rectangle. So go ahead, find your estimate, put your answer here, and then answer, is your answer precise? And how does where you rounded your answer affect the precision of your answer? All right, so when we're thinking about the area of this rectangle, we expect that you thought about the fact that the square root of 3 is going to be your length, the square root of 2 is going to be your width, and what we need to do is multiply those together, right? Multiply the square root of 3 by the square root of 2. But how do we actually multiply the square root of 3 and the square root of 2? We did go over this in class, and you guys know that this is the square root of 6. But when we think about what the square root of 6 actually is, we know that this is an irrational number. It's a decimal that goes on forever. And that's not very easy for us to work with. So today we're going to work with how can we get as close to the square root of 6 as possible by just using decimals. A lot of this discussion is going to revolve around this idea of precision. And precision is how close are we to the actual answer. So in this box here, if you didn't already, you want to make sure that you talk about how close is your answer, the answer that you got, right? You may have gotten a decimal here. How close is your answer to the actual square root of 6? All right, let's jump into a little bit of a discussion here. And this discussion is going to focus on how can we approximate the area of this box, even though both of these numbers, the square root of 3 and the square root of 2, are irrational numbers with decimals that go on forever. The first thing we're going to do is a process called finding a lower approximation. So a lower approximation is an estimate of an area found by rounding down, right? A lower approximation, your answer will always be lower than the exact answer. And our goal is to be as precise as possible. So when I do this lower approximation, I'm going to round at different intervals on my number and get closer and closer and closer to the exact answer. So before I can round the square root of 2, the square root of 3, and the square root of 6, I need to know what the square root of 2, the square root of 3, and the square root of 6 are, right? So in this first column, we're going to be working with the square root of 2. In the second column, we'll be working with the square root of 3. And in the last column, we'll be working with the actual area, which we know is the square root of 6. So the square root of 2 is 1.414213, and so on. We can figure that out by putting this into our calculator. The square root of 3 is 1.732050, and so on. We can figure that out by putting the square root of 3 into our calculator. And the square root of 6 is 2.4494897, and so on. So when we do a lower approximation, we'll be perpetually rounding down. So that means that we're going to take our first digit, which in this case is 1, and we're going to round down, which means we're just going to leave it the same. So here we have 1 and 1. Now, what area are we actually finding if we round down to just look at 1 instead of looking at 1.4 and 1.7 and so on? Right? So what is that area? It's if we mark our graph at 1 and at 1, this is the area that we're actually finding when we do that first approximation. Now we see that when we multiply 1 and 1, we get 1, but this area is not anywhere near the actual area that we need. So instead of working with this area, we're going to do a little bit of a better approximation, and we're going to try with 2 digits instead. See if we can get closer to the actual area that we're trying to find. So when we do that little bit better, we're going to take our first 2 digits instead of our first digit. So we're going to take 1.4 and 1.7. So 1.4, 1.7, we get 2.38. So on our graph, 1.4 is right here. 1.7 is right here. So we can see that though we're not exactly to our actual area yet, we are getting pretty close. And this is much closer than our initial approximation of 1 was. Now we're going to keep going. And in our third row, you probably guessed, we're going to be using 3 digits instead of 2 digits. So here we'll be doing 1.73. And when we do 1.41 times 1.73, we get 2.4393 as our answer. And again, we're getting closer and closer and closer to our actual area, which we know is the square root of 6. So right now, I'd like you to pause this video and take your time to fill out the empty spaces in this chart. Thanks for taking a moment to do that. Now, what you should notice is that as we move down our chart, our numbers are getting closer and closer to our actual values. So even though the square root of 2 is an irrational number, as we add more and more decimal places onto the end, we're getting more and more precise. The same thing with the square root of 3. As we add more and more decimal places onto our number, we're getting more and more precise. If our sides are getting more precise, that means that our answer, our square root of 6 answer, is actually getting more precise too. So if I compare 1 to 2.4, those are pretty far away. But if I compare 2.449487 to 2.449489, that's pretty close. We're getting closer and closer and closer to what our actual answer is. This is a lower approximation because if we look at all of our answers, they are all lower than our actual final answer. Now let's do the same thing, but this time we're going to be using an upper approximation. So the definition of an upper approximation is an estimate of area found by rounding up, and our answers will always be higher than the correct answer or than the exact answer. Our goal is to be as precise as possible. So here, instead of rounding down like when we did the lower approximation, we'll be rounding up. So I'm just going to take a moment, fill in my square root of 2, my square root of 3, and my square root of 6. So when I find my sides for my first approximation, I'm going to just take the first digit of each one, but instead of leaving that alone, I'm going to round up. So 1 rounds up to 2, and my second one rounds up to 2. When I multiply those, I get 4. Now, what area am I actually talking about when I do that? Well, if instead of the square root of 3, I'm using 2, and instead of the square root of 2, I'm using 2, this is the area that I'm finding. Now we can see that that area is much too large, and we need to get closer to our exact area. So how are we going to do that? Well, we're just going to use more digits from our irrational numbers. So if I look at the square root of 2, my next digit is 1.4. So instead of 1.4, I'm going to use 1.5. For the square root of 3, instead of 1.7, I'm going to use 1.8. Remember, I'm doing an upper approximation, so I'm rounding up. So 1.4 becomes 1.5, and 1.7 becomes 1.8. So now, this is the area that I'm finding, which, again, is not quite exact, but is significantly closer to my actual area than my previous estimate was. When I multiply 1.5 times 1.8, I get 2.7. So that means that the area of the red box is 2.7. And this is an estimate that is closer to the actual area than my first estimate was. Our next one is already done for us. They were using 3 digits. So instead of 1.41, they used 1.42. And instead of 1.73, they used 1.74. And when they multiplied those, they got this answer at the end. All right, take a moment, pause this video, and fill out the empty areas of your chart. Thanks for working on that. If you did this correctly, you should see a similar pattern here that you saw when you did your first chart. So as we go down our chart, we should be getting closer and closer and closer to our actual number at the bottom. That should be true for all of our columns. But the really important column is this last one. We'll see that we started out with 4, which is very far away from our actual area. But then eventually we got to 2.44949, which is almost exactly our actual area here. So we know that as we're using more and more decimals, we're getting more and more precise. Our last problem is this discussion question that is asking, how can we estimate the area of a curved figure? So what I would like you to do is pause this video, take a moment, and answer this question with an idea that you have on your own. So what do you think is one way that we can estimate the area of a curved figure? Thanks for taking a moment to do that. There are many ways to estimate the area of a curved figure, but today what we're going to do is use polygonal areas. Now, a polygonal area is simply a shape with straight sides. So we're going to take a shape that we know how to find the area of it, and we're going to put it inside this one to estimate what the area actually is. So a lower estimate, remember when we did a lower estimate before, we were looking for a shape that's smaller than our actual shape, right? Lower estimates are always too small. So what we're going to do is we're going to put a shape inside of this. This is called an ellipse. So we're going to take a shape, we're going to put it inside of this ellipse to figure out what's a lower end of what our size could be. So if I look at this area, I'm going to pick a point on my shape, and I either want to be using half boxes or whole boxes to make my polygonal area, just to make it easy on myself, because those are easy things to count. So when I'm making my shape, it has to be completely inside of this ellipse. So I'm going to go to the next cross section that is inside of my shape. So that's going to be a half box. I went half diagonally. Now I can't go out here because it's outside of my shape, right? I can't go out there. So instead, I'm going to go to the next cross section that's inside my shape. Now I can't go out here because it's outside my shape. So instead I'm going to go inside. And this involves me going straight across. I wish I could go out here because it's really close, right? But it's still outside my shape, so I can't do that. So I'm going to go straight across. And then this one I can go diagonally because that one's right on the edge. I'm going to continue doing that around my entire shape. All right, so this is the actual shape that I'm going to use to estimate my area. And the reason why this shape is so useful is because we've got a bunch of whole boxes. I'm going to give you a moment where you can count them. I'm also going to count them quickly. Okay, so to me it looks like we have 28 whole boxes. And then I've also got a bunch of half boxes around here, right? These boxes that I cut in half by making them triangles. That's half of a box. Here's another half of a box. If I put those together, I get one whole box, right? So that's one pair. Here's another pair. Here's a pair together. Here's another pair together. Here's a pair. And here's one more pair together. So that's 1, 2, 3, 4. That's 6 pairs. 28 plus 6, that's 34. So that means that in total, this area is 34 units because I have 28 whole squares, and then I have 6 squares that are made up of the half squares together. Okay, so this is a lower estimate, right? And we know that this is too small because we can see that this shape that we found the area of is significantly smaller than the actual shape that we're looking at. But right now, it's the best we can do. Now let's try to find an upper estimate. I'm going to erase what I have and we're going to start over, but this time we're going to be working outside of our shape. So to find that upper estimate, we'll still make a polygonal area. We'll still make something that has whole and half squares only, but this time we'll be doing it outside of our shape instead of inside of our shape. I'm going to start at the same point, but instead of going inside of my shape to this point, I'm going to go outside along the edge. Now here, this point is now outside, so I can go to that point. But I can't go across to this one, so I'm going to have to go up to this one. And I'm going to cut across. And I just need to make sure that I'm staying outside of my shape. The idea here is that I got as close as possible to the actual shape, but I stayed outside of it. So let's do the same thing we did before and count how many squares do we have that are inside of this shape. All right, so I count that we have 48 squares inside of the black shape that I made. Now, how many half squares do we have? I'm going to count these in red one more time. So here are 2 half squares that together make one whole. Here are another 2 that make a whole. One more pair, and the last pair. So if I put those 4 pairs together, I end up with 4 whole squares. And if I add those, I get 52. So that means that I know that 34 is too small, and I know that 52 is too big. So if I wanted to guess, what is the actual size? I would guess somewhere in between 34 and 52. So it looks to me like the outside one was a little bit closer to the actual shape than the inside one was. So maybe I guess that it's like 45-ish, right? It's about 45, maybe it's 48, maybe it's 43, right? But it's somewhere in between 34 and 52. So this is the end of our notes. What you need to do to finish up is fill in this box with an opinion of your own, and then continue on to work on the practice problems. If you have any questions on those practice problems, you can leave them in the comments on this video, you can ask them on Google Classroom, or you can attend a coach class online. Good luck.